26,000 light-years away, something is pulsing at the center of our galaxy, a glowing sphere of high-energy light, 5,000 light-years wide, radio signals that appear from nowhere and vanish. Stars hurled out of the galactic core at speeds that let them outrun our entire galaxy. Scientists have no agreed explanation for any of it. We will cover the invisible dust wall, hiding it all, the dead stars spinning 100 times a second, the dark matter theory that could change physics forever, and the signal no one can identify. If you enjoy this journey, subscribe and leave a like. Now brace yourself. We begin. Point your eyes at the night sky on a clear night. Find the thick river of stars stretching from one horizon to the other. That band is the Milky Way, your home galaxy, seen from the inside. Now, try to find the center of it. You cannot. A wall stands between you and it, and that wall is made of dust. The center of our galaxy sits 26,000 light-years away from Earth. To picture that distance, imagine the gap between New York and Los Angeles. Now stack that gap side by side, roughly 9 million times. That is how far the galactic center is, and every single inch of that path is packed with clouds of interstellar dust so thick that visible light cannot punch through them. Visible light is what your eyes detect. It is what cameras capture. It is how every painting and photograph of space was made for most of human history. And for the galactic center, visible light is completely useless. The dust eats it, absorbs it. The core of our own galaxy was effectively invisible to us for centuries. Astronomers first began to suspect something massive was hiding behind that curtain in the early 1900s. They noticed a strange dark lane cutting through the bright band of stars in the sky. Regions where stars simply stopped, they called them dark nebulae, assuming they were empty patches of space. It took decades to figure out the truth. Those dark patches were full of material, dense, cold clouds of carbon, silicates, and ice grains, a cosmic fog bank stretching thousands of light-years deep. The breakthrough came when scientists realized that other types of light could pass through what visible light could not. Radio waves travel straight through the dust. Infrared light, which carries heat, slips through as well. X-rays, generated by the most violent events in the universe, punch right through. When astronomers aimed telescopes tuned to these wavelengths at the dark lane in the sky, the wall became transparent. What they saw on the other side stopped them cold, a region unlike anything in the outer parts of the galaxy. Stars packed so tightly that if you lived on a planet near the galactic center, your night sky would never be dark. Thousands of stars would blaze overhead at all times, some of them ancient, some brand new. All of them crowded into a space smaller than the distance between our sun and its nearest neighboring star. And at the absolute center of all of it, something pulling everything inward. A gravity source so powerful that stars orbited it the way planets orbit a sun, except instead of taking hundreds of millions of years to complete one loop, some of those stars finished their orbits in just a few years. A few years. The numbers implied a mass millions of times greater than our entire sun, compressed into a space you could drop inside the orbit of Mercury. Astronomers mapped the dust layers. They calibrated their instruments. They calculated the distance, the density, the mass hidden behind the curtain. And the more they looked, the stranger it got. The dust wall was not just blocking light. Something behind it was generating signals that did not fit any known category. Something was pulsing, glowing, venting, and throwing stars across the galaxy at impossible speeds. Scientists had spent a century learning to see through the wall. What they found once they could see clearly raised questions far harder than the wall itself. The next piece of the puzzle sits right at the center, and it is 4 million times heavier than the Sunday. It has no light of its own. It emits nothing you can see with your eyes, yet it controls the fate of every single star in our galaxy, including our Sunday. Its name is Sagittarius A star, and it is the supermassive black hole sitting at the exact center of the Milky Way. A black hole forms when a massive star collapses under its own weight at the end of its life. The core gets crushed so completely that gravity becomes infinite at its center. Space itself curves inward around it so sharply that nothing, not even light, can escape once it crosses a certain boundary. That boundary is called the event horizon, the point of no return. Sagittarius A star is not a regular black hole. Regular black holes, the kind born from single dying stars, weigh between 5 and 50 times the mass of our Sunday. Sagittarius. A star weighs 4 million times the mass of our Sunday. It is a supermassive black hole, and every large galaxy in the known universe appears to have one sitting at its core. If you compress the entire Sun into a black hole, it would be about 3 miles across. Sagittarius A star, despite being 4 million times heavier, fits inside a sphere roughly the size of the distance between Earth and the Sunday. That is the nature of extreme gravity. It folds space inward so tightly that unimaginable mass occupies a shockingly small volume. Now here is the strange part. For something that massive, Sagittarius A star is almost completely quiet. Active black holes in other galaxies shoot jets of plasma millions of light years long. They blaze with radiation. They can outshine every star in their galaxy combined. Those are called active galactic nuclei, and astronomers can detect them from billions of light years away. Sagittarius A star does almost none of that. It occasionally flares. A small burst of X-rays here, a brief spike in infrared light there. But compared to the violent black holes in other galaxies, ours sits in near silence. That silence makes the unexplained signals coming from its neighborhood even harder to dismiss. Astronomers began mapping the stars closest to Sagittarius A star in the 1990s. They tracked individual stars over many years, watching them trace curved paths across the sky. When they plotted those paths, the orbits all pointed to the same invisible center. One star, labeled S2 by researchers, completes a full orbit around the black hole in just 16 years. To do that, it reaches speeds of about 5,000 miles per second at its closest approach. 5,000 miles per second. That is fast enough to cross the entire United States in less than a single second. Those measurements gave scientists the most precise estimate yet of the black hole's mass. 4.1 million times the mass of our Sun, packed into a region of space smaller than our solar system. But even after all those measurements, after all those years of tracking stars and mapping orbits, one question kept growing louder. If the black hole is this massive and this central to our galaxy, why is it so quiet? Where is the energy going? And what is producing all the unexplained radiation erupting from the space around it? Scientists thought they understood the beast at the center. Then a group of stars changed everything, and they have been trying to keep up ever since. Imagine standing on a track at your school. Now imagine running that track so fast that you complete a full lap in 16 years, swinging around a turn so tight that you are only a few billion miles from an object 4 million times heavier than the Sunday. That is the life of the stars known as the stars, and studying them gave scientists the clearest look yet at the monster in the center of our galaxy. The stars are a cluster of young, massive, brilliant stars orbiting extremely close to Sagittarius A star. They do not orbit slowly the way Earth orbits our Sun, taking a comfortable 365 days to complete one loop. These stars move at speeds that make our solar system look frozen. Astronomers have tracked dozens of them over the past 3 decades using infrared telescopes that can see through the dust wall. The star called S2 became the most studied of them all. For years, astronomers at observatories in Europe and Chile watched S2 trace an elliptical path around the invisible center. In 2018, S2 made its closest approach to the black hole. At that moment, it was traveling at about 5,000 miles per second and came within a distance of roughly 120 times the gap between Earth and Sunday. That closest approach did something remarkable. It tested a prediction made by Albert Einstein over 100 years ago. Einstein's general theory of relativity says that space and time warp around massive objects. The bigger the mass, the bigger the warp. One specific prediction is called gravitational redshift. When light climbs out of an intense gravitational field, it loses energy and shifts toward the red end of the color spectrum. As S2 screamed past the black hole and its light traveled back toward Earth, astronomers measured exactly that shift. The prediction matched the measurement almost perfectly, a 100-year-old equation confirmed by watching a single star race around a black hole 26,000 light-years away. But the stars raised a mystery alongside that triumph. These are young stars, hot, bright, and freshly formed by cosmic standards. Stars like them typically form in dense gas clouds far from any black hole, where gravity pulls material together slowly over millions of years. Near a supermassive black hole, the gravitational forces are so extreme they should shred any gas cloud before it can collapse into a star. So how did these stars get there? Astronomers offered two possibilities. Either the stars formed far away and migrated inward over time, nudged by gravitational interactions with other objects. Or, more radically, something about the extreme environment near the black hole actually allows star formation in ways current physics cannot fully explain. Neither answer is settled. Both camps have evidence. Both camps have problems. What made it stranger still was the discovery that some stars appeared to be on orbits tilted at wild angles compared to each other, as if they had arrived from completely different directions at completely different times. The black hole was not surrounded by a single orderly disk of stars. It was surrounded by a chaotic, overlapping swarm, and swirling in between those stars, filling the space between their orbits, were signals, radio signals, gamma-ray pulses, energetic flares with no obvious source. The stars were orbiting something, and that something was doing far more than just sitting there. The next discovery would shake the entire field, and it started with an unexpected beat. In the early 2000s, radio astronomers were doing what they always do, scanning the sky and cataloging signals. Most signals behave predictably. A pulsar spins and pulses like clockwork. A quasar blazes steadily. Background radiation hums at the same frequency everywhere. The cosmos, for all its violence, follows patterns. Then something from the direction of the galactic center broke the pattern. A group of signals started appearing in the data. They were labeled galactic center radio transients, which is the scientific way of saying radio pulses from the galactic center that appear and disappear without explanation. The pulses were short, they were bright, and they did not match any known object. Radio telescopes work by collecting radio waves, which are a form of light invisible to human eyes, but detectable by large dish antennas. When astronomers analyze a radio signal, they look at its brightness, its frequency, how long it lasts, and whether it repeats. Every known type of object in space has a signature. Pulsars pulse in milliseconds. Quasars are consistent across years. Flaring stars change slowly over days. These new signals from the galactic center fit none of those signatures. Some lasted minutes. Some lasted hours. Some appeared once and never showed up again. Some repeated, but at irregular intervals that could not be predicted. And they were coming from one of the most extreme environments in the galaxy, a region where the gravitational and magnetic forces are orders of magnitude more intense than anything in our corner of the Milky Way. Scientists began logging the signals and comparing notes. The data was puzzling enough that some researchers started checking their instruments, assuming equipment errors. The signals kept coming, clean, consistent in their inconsistency. The strange thing about a transient signal is that it forces you to decide whether it is a new type of object or a known object behaving in a completely unexpected way. Both options are unsettling. If it is a new type of object, your entire catalogue of known cosmic phenomena is incomplete. If it is a known object, then something about the environment near the galactic center is producing behavior that your models cannot predict. Astronomers leaned toward the second option first. Maybe these were magnetars, a rare class of neutron star with magnetic fields so intense they can warp the fabric of atoms. Magnetars do produce bursts of radio energy, but the galactic center signals did not match magnetar timing. They were too slow, too irregular. Magnetars tend to burst fast and fade fast. So maybe they were flare stars, ordinary stars with extreme magnetic activity that produces sudden bright radio flashes. But flare stars have other signatures in X-ray and visible light. These galactic center signals were invisible in those wavelengths. Every explanation ran into a wall. What made it worse was the location. The galactic center is not just energetic, it is noisy. Signals from that region are blurred and scrambled by the dense clouds of charged particles sitting between Earth and the core. Separating one signal from the background chaos is like trying to hear a whisper at a concert. Astronomers were certain they were only catching a fraction of what was actually happening. A few years into logging these transients, a bigger instrument aimed itself at the sky. And in 2009, it found something so large and so bright that ignoring it became impossible. On June 11, 2008, a spacecraft the size of a school bus launched from Cape Canaveral on top of a Delta II rocket. It climbed into low Earth orbit, deployed its solar panels, and began scanning the entire sky once every 3 hours. Its name was the Fermi Gamma Ray Space Telescope. Its job was to map the highest energy light in the universe. Gamma rays are produced by the most violent events in the cosmos: exploding stars, colliding neutron stars, matter falling into black holes. The energy in a single gamma ray photon is millions of times greater than the energy in a photon of visible light. Nothing gentle produces gamma rays. They are the signature of extreme physics. For its first year, Fermi built up a map of gamma-ray sources across the entire sky. Scientists expected to find known sources, supernova remnants, pulsars, active black holes in distant galaxies. They found all of those. And then, buried in the data pointing toward the center of our own galaxy, they found something that did not belong. A glow, a massive, roughly spherical glow of gamma rays centered on the galactic center and spreading outward in every direction. Astronomers called it the Galactic Center GVXS, with GV referring to the energy level of the photons involved. The word excess means the signal was above and beyond anything that known sources in that region could explain. Researchers accounted for every pulsar, every supernova remnant, every patch of hot gas they knew existed near the galactic center. They subtracted all of those contributions from the data. The glow remained 5,000 light-years across, stretching in every direction from the central black hole like a ghostly sphere of pure energy. That is enormous. To put it in scale, our entire solar system is less than a single light day across. This sphere was 5,000 light-years in every direction. Stacked football fields would not get you started on measuring it. And every particle of light inside that sphere carried an energy signature in a very specific range, not scattered randomly across all energy levels the way most sources produce. Concentrated, peaked, like a specific process was producing it over and over again at the same energy output. That specificity is what made astronomers stop. Random, chaotic processes produce light across a wide range of energies, but peaked, concentrated signals in a narrow energy band suggest something repeatable, something governed by a rule. And when scientists looked at what known physics could produce a gamma-ray glow with that exact energy profile, centered on the densest concentration of mass in the galaxy, two candidates emerged. The first candidate involved something scientists had spent decades predicting but never directly observed, something invisible, something that might make up most of the mass in the entire universe. The second candidate involved thousands of dead stars spinning so fast they were on the edge of tearing themselves apart. Both explanations were extraordinary, and the data could support either one. The The field split down the middle, two camps formed, and the argument between them is still burning today. Before we get to the debate, you need to understand what exactly the glow could be made of, because the first theory reaches far beyond our galaxy, deep into the fabric of the universe itself. Stand outside on a clear night and look up. Every dot of light you see is producing visible light, the kind your eyes evolved to detect. Stars burn hydrogen and release that energy as light across a wide range of colors. That is the version of the universe humans have always been able to see. The universe your eyes cannot see is far more violent. Gamma rays sit at the extreme end of the electromagnetic spectrum, the scale that organizes all types of light by energy level. Radio waves are at the low energy end, the kind used by cell towers and satellites. Visible light sits in the middle. Ultraviolet light, X-rays, and gamma rays climb higher and higher from there. A single gamma ray photon carries so much energy it can pass through several inches of lead. These are not gentle waves of light. They are bullets of pure energy. Producing gamma rays requires violence on a cosmic scale. When a massive star explodes as a supernova, the shock wave accelerates particles to extreme speeds and produces gamma rays. When matter falls into a black hole and reaches the threshold of no return, it releases gamma rays. When two neutron stars collide, the collision announces itself with a blast of gamma rays powerful enough to outshine entire galaxies for a fraction of a second. So when the Fermi telescope detected a spherical glow of gamma rays surrounding the galactic center, it was detecting the aftermath of something enormously energetic happening inside that sphere, repeatedly over a vast region of space. The energy level of the photons in the glow sits in a very specific range. Researchers measured it carefully. When they plotted the brightness of the glow against the energy of each photon, the graph peaked at a specific point. That peak was not arbitrary. It matched the energy level that would be released if a specific type of particle annihilated with its own antiparticle. Annihilation is exactly what the word suggests. When a particle meets its antimatter twin, both particles are completely destroyed. All of their mass converts instantly to energy, released as photons. The photons carry away the energy equivalent of both particles' combined mass, converted according to Einstein's mass-energy equation. And the energy of those photons is fixed, predictable. It depends only on the mass of the original particles. The glow's energy profile pointed to a particle with a mass in a range that physicists had been predicting for decades. A particle heavy enough and slow-moving enough to have clumped in enormous quantities at the gravitational center of the galaxy over billions of years. A particle that produces no light of its own. A particle that passes through ordinary matter almost without interacting with it at all. A particle that, if it existed, would explain one of the biggest unsolved problems in all of science. The sphere surrounding Sagittarius A star was glowing in exactly the way that particle would glow if enormous numbers of them were crashing into each other and annihilating deep inside the gravitational heart of our galaxy. The name for this particle is a weakly interacting massive particle. And if the galactic center glow turns out to be caused by them annihilating, it would be the most significant scientific discovery in human history. The proof would explain why galaxies hold together, why the universe has the structure it does, and what the invisible majority of all matter in existence actually is. That proof might already be sitting in the Fermi data. Scientists are still fighting over whether to believe it. Every galaxy you have ever seen in a photograph is lying to you. The stars, the gas, the glowing dust, all of that visible material accounts for only a fraction of what is actually there. The rest is invisible. It emits no light. It absorbs no light. Telescopes cannot detect it directly, and yet it is everywhere, threaded through the fabric of every galaxy, holding them together with gravity that visible matter alone cannot explain. Scientists call it dark matter, and it makes up roughly 85% of all the matter in the universe. The evidence for dark matter's existence is overwhelming. Galaxies rotate in ways that only make sense if there is far more mass present than we can see. When galaxies cluster together, the way they bend the light of more distant objects behind them reveals mass that has no visible source. When scientists model the large-scale structure of the universe, the web of galaxy filaments and giant cosmic voids only forms correctly if dark matter is included. Take it out of the simulation, and the universe looks nothing like what we observe. But for all that evidence, no one has ever directly detected a dark matter particle. No experiment has caught one. No telescope has photographed one. Dark matter leaves only gravitational fingerprints. Weakly interacting massive particles are the leading candidate. Scientists have spent decades building underground detectors, trying to catch a weakly interacting massive particle colliding with an atomic nucleus. The detectors are buried deep underground to block interference from cosmic rays. They are chilled to temperatures near absolute zero to reduce noise. They have been running for years. So far, no confirmed detection. The Galactic Center offers a different approach. The center of our galaxy is the place in the Milky Way where gravity has had billions of years to pull dark matter inward and concentrate it into a dense cloud. If weakly interacting massive particles exist and they accumulate at the galactic center, they will occasionally collide with each other, and when two of them collide, they annihilate, converting their combined mass entirely into energy, released as gamma rays at a very specific energy level. That energy level matches the glow Fermi detected. A team of researchers analyzed the Fermi data carefully, subtracting every known source of gamma rays they could identify in the galactic center region. After all those subtractions, the excess glow remained. Its energy profile matched the annihilation signal predicted by weakly interacting massive particle models. Its spatial distribution matched what you would expect from dark matter concentrated around a supermassive black hole. The match was not approximate, it was precise. If the interpretation is correct, the galactic center has been producing evidence for dark matter for billions of years, broadcasting it across the galaxy in the form of a glowing sphere of gamma rays, and humanity only became sensitive enough to detect it in 2009. Proving dark matter detection would not just win a Nobel Prize. It would answer questions about why stars can orbit galaxies without flying apart, why galaxy clusters bend light the way they do, and what the universe is actually built from at its most fundamental level. But the evidence is not conclusive. It fits the dark matter model. It also fits something else entirely. And the team arguing for that alternative has data just as compelling, pointing to a completely different explanation hidden inside the chaos of the galactic center. You are made of atoms. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. This chain of smaller and smaller pieces is the foundation of everything you have ever touched, seen, or tasted. The entire periodic table of elements, every rock, every star, every galaxy visible through any telescope, is built from this same family of particles. Scientists call this family ordinary matter, or baryonic matter, and it accounts for only about 15% of all the matter in the universe. The rest is weakly interacting massive particles, or something like them. The phrase weakly interacting has a technical meaning in physics. It refers to particles that only respond to two of the four fundamental forces: gravity and the weak nuclear force. They do not respond to electromagnetism, which means they produce no light and absorb no light. They do not respond to the strong nuclear force, which binds atomic nuclei together. They pass through ordinary matter almost without touching it. Picture trillions of invisible particles streaming through the room right now, through the walls, through the floor, through your body, through Earth itself. They travel in every direction at all times, and almost nothing stops them. Occasionally, extremely rarely, one of them bumps into an atomic nucleus and leaves a tiny trace of energy. That tiny trace is what underground detectors are trying to catch. To detect these particles directly, scientists built some of the most sensitive instruments in human history. One facility sits beneath a mountain in Italy, shielded from cosmic rays by nearly a mile of solid rock. Another is buried in an old gold mine in South Dakota, more than a mile underground. These detectors contain tanks of ultra-pure materials, chilled to just above absolute zero, designed to register the faintest possible disturbance from a passing particle. After years of operation, no confirmed detection. That failure does not mean the particles do not exist. It means they interact even more weakly than the most optimistic models predicted. The underground detectors were built based on early estimates of interaction strength. Those estimates may simply have been wrong. Meanwhile, indirect evidence keeps accumulating. The energy profile of the galactic center glow continues to match annihilation predictions. In 2026, a new analysis linked a very specific energy signature, known as the 511 kiloelectron-volt emission line, to 3 separate unexplained signals near the galactic center simultaneously. That emission line is exactly what you would expect from certain dark matter models where the particles enter an excited state before annihilating. 3 signals, same energy, same region, same prediction. Scientists who have spent their careers on dark matter models called it the strongest indirect evidence yet. Scientists who support the alternative explanation called it a coincidence that fits their model just as well. That alternative involves a completely different population of objects, dense, spinning, dead, and hiding in the galactic core in numbers that should have been impossible to miss. Except somehow, until recently, we did miss them. And when astronomers started calculating how many of them would need to exist to produce the glow, the answer was staggering. Somewhere in the chaos surrounding Sagittarius A star, hidden behind the dust wall and drowned in the general noise of one of the most energetic environments in the galaxy, there may be an army of dead stars. Thousands of them, all spinning, all ancient, all producing beams of radiation that, added together, could account for the entire gamma-ray glow that Fermi detected. This is the pulsar population hypothesis, and it is the main rival to the dark matter explanation. To understand it, you need to know what a pulsar is. When a star much more massive than our Sun runs out of fuel, it explodes as a supernova. The outer layers blast outward as a shockwave. The core, left behind, collapses under gravity so intense that electrons and protons merge together, forming neutrons. The result is a neutron star, an object roughly the mass of our Sun, compressed into a sphere about the size of a city, roughly 12 miles across. Imagine compressing the entire Sun, which is about 865,000 miles wide, down to something the size of San Francisco. The density is so extreme that a single teaspoon of neutron star material would weigh about 1 billion tons. Neutron stars spin, all stars spin, and when their cores collapse, they conserve angular momentum the same way a spinning ice skater speeds up when pulling in their arms. The collapse amplifies the rotation dramatically. Some neutron stars spin hundreds of times per second. As they spin, their powerful magnetic fields sweep beams of radiation through space. If one of those beams sweeps past Earth, radio telescopes detect a repeating pulse. These are pulsars. Millisecond pulsars are a specific type. They spin between 100 and 700 times per second. Their equators bulge outward under the centrifugal force. The material at their surfaces is moving so fast that these objects are technically close to the limit of physical stability. They are the fastest spinning solid objects in the known universe. The galactic center is an ancient environment. Billions of years of stellar birth and death have left behind enormous numbers of stellar corpses. Neutron stars, white dwarfs, and black holes all accumulate over time in the central region, drawn inward by the gravity of Sagittarius A star. A research team ran calculations on how many millisecond pulsars could plausibly exist in the central bulge of the galaxy, given the estimated history of star formation there. The number they arrived at was in the thousands, possibly tens of thousands. A single millisecond pulsar produces gamma rays as part of its emission. 1,000 of them crammed into a region surrounding the galactic center, would collectively produce a gamma-ray glow with a spatial distribution and energy profile that looks remarkably similar to what Fermi detected. The match is close enough to be a serious challenge to the dark matter interpretation. But there is a problem. Astronomers have identified only a handful of millisecond pulsars anywhere near the galactic center. Detecting individual pulsars in that region is extraordinarily difficult. The dense plasma between Earth and the core smears out the sharp pulses that normally make pulsars easy to identify at a distance. The army could be real and essentially invisible to current instruments. That invisibility cuts both ways. Scientists cannot confirm the pulsars are there. They cannot rule them out either. The debate depends on which explanation you find more plausible, and the answer may require instruments that do not exist yet. Both possibilities, an army of dead stars or a sea of annihilating dark matter, point to a galactic center far more extreme than anyone imagined 30 years ago. But then, a completely different signal showed up, one that neither theory predicted. A neutron star the mass of our sun, compressed to the size of a city, spinning 700 times per second. The math alone is almost impossible to hold in your mind. But the physics of how these objects reach that speed, and what happens to them at their limit, is where the story gets genuinely strange. All rotating objects want to conserve angular momentum. A figure skater pulling their arms inward spins faster. Earth itself spins because the cloud of gas and dust it formed from was rotating, and the collapse preserved that spin. Stars are the same. They rotate, some slowly, some quickly. When a massive star's core collapses into a neutron star at the end of its life, the rotation speeds up drastically. For the same reason the skater speeds up. The collapsing object shrinks by a factor of roughly 50,000 in radius. The spin amplifies accordingly. Most pulsars born this way spin fast, then gradually slow down as they radiate energy. Within millions of years, many of them slow to a crawl. So where do millisecond pulsars come from? Their spin rates should be long gone. The answer is a companion star. Millisecond pulsars almost always exist in binary systems, pairs of objects orbiting each other. The neutron star and a companion star orbit their shared center of gravity. Over time, the neutron star's gravity pulls material from the companion's outer layers. That material falls onto the neutron star in a spiraling disk, carrying angular momentum with it. Over millions of years, that steady transfer of angular momentum spins the neutron star back up, re-accelerating it to hundreds of rotations per second. Astronomers call this process recycling. The neutron star gets a second life, spun back up to speeds it had only briefly at birth. At 700 rotations per second, the equator of a millisecond pulsar is moving at a significant fraction of the speed of light. The material at the surface is under centrifugal stress, strong enough to threaten the structural integrity of the star. Scientists have calculated the maximum possible spin rate for a neutron star before it starts flinging matter off its surface and tearing itself apart. That limit sits somewhere above 1,000 rotations per second. No millisecond pulsar found so far has reached that limit. They cluster below it, whether by chance or because some physical braking mechanism prevents them from spinning quite that fast, is a question without a clear answer. What millisecond pulsars do at these speeds is produce intense radiation. Their magnetic fields, still enormously strong from their birth, sweep powerful beams of radio waves, X-rays, and gamma rays through space with every rotation. The gamma rays they produce fall in the same energy range as the galactic center glow detected by Fermi. A single one contributes a small amount. Thousands of them, concentrated in the central region, could collectively produce a glow indistinguishable from the dark matter annihilation signal by current instruments. The catch is detecting them individually. In quieter regions of the galaxy, pulsars stand out because their pulses arrive in sharp, regular bursts. Near the galactic center, the plasma smears those pulses out during the long journey to Earth. They arrive softened, blurred, harder to separate from background noise. The army may be hiding in plain signal, invisible not because they are absent, but because the environment itself is scrambling their signatures. Scientists are building new instruments to cut through that scrambling. Until then, both the dark matter camp and the pulsar camp can look at the same data and see evidence for their own theory. And that deadlock is exactly what made the next discovery so alarming, because it came from a completely different direction. Two theories, one observation, a decade and a half of argument. The debate over the galactic center gamma ray excess has split the astrophysics community in ways that rarely happen in science. And the reason it has lasted so long is that both sides have genuinely strong evidence. Start with the dark matter camp. Their strongest argument is the shape of the glow. The excess light detected by Fermi does not just come from one point near the center. It spreads outward in a spherical distribution that follows a specific mathematical pattern called a squared density profile. Dark matter models predict exactly this pattern, because dark matter falls inward under gravity and concentrates toward the center, but in a smooth, spherical cloud rather than a flat disk. The shape of the glow matches the shape you would expect from a dark matter cloud centered on Sagittarius A star. That match is extremely difficult to explain if the source is pulsars, which would be scattered in a slightly different distribution reflecting the history of star formation in the central bulge. Now, the pulsar camp, their strongest argument is a technique called wavelet analysis, which breaks signals down into their spatial components the same way a prism breaks light into colors. When researchers applied this technique to the Fermi data in the late 2010s, they found hints that the glow was slightly uneven. It showed faint statistical graininess consistent with the signal coming from many individual point sources spread across the region, rather than one smooth, continuous cloud. Point sources are what you would expect from thousands of individual pulsars. A truly smooth dark matter annihilation signal should look more uniform. The dark matter camp responded that the graininess was within the noise level of the data and could not be trusted. The pulsar camp responded that the shape argument worked in reverse too, since the stellar population of the central bulge has not been mapped precisely enough to rule out a pulsar distribution that could mimic the dark matter profile. Back and forth, year after year, in the background, a third variable started making itself known. The energy profile of the glow is important, because the peak energy tells you something about the mass of the particle producing it if the source is dark matter. But the peak energy of the galactic center excess shifted slightly in different analyses, depending on which known sources researchers subtracted first, which instrument calibration they used, and which energy range they focused on. Small changes in methodology produced slightly different peak energies. That instability is either a sign that the signal is messier than a clean dark matter annihilation would produce, or a sign that the data analysis is just difficult in one of the noisiest regions of the sky. Neither side has landed a decisive blow. The standoff has pushed researchers toward building better telescopes, refining their data analysis methods, and looking for any additional signal that might break the tie. Then, in 2020, something entirely new entered the picture. A signal that neither camp had predicted. A radio source that blinked on from the direction of the galactic center and then disappeared. And when astronomers looked at its properties, they realized they had no category for it at all. In 2020, a radio telescope network spread across the Australian outback was doing what it was built to do, scanning the sky in radio wavelengths across enormous patches of space. The network is called the Australian Square Kilometre Array Pathfinder, a grid of dish antennas spread across the desert, working together to build a detailed radio map of the southern sky. Buried in one of those maps, researchers spotted a radio source they had never seen before. It was coming from the direction of the galactic center. It was bright, and it was doing something no known type of cosmic object does in quite the same way. The source pulsed for weeks. Then it went silent. Then it appeared again weeks later, pulsing. Then it vanished again. Over the course of the observation period, the research team detected it 6 separate times, each appearance lasting weeks, each disappearance complete. Between active phases, the source was gone entirely. No faint trace, no dimming tail, just nothing. The researchers who analyzed the data named it after the team member who first identified it in the observations. Its official catalog name is a long string of numbers and coordinates, so people simply call it Andy's object. The first strange feature is the duration. Most transient radio sources in space are brief. Pulsars produce millisecond pulses. Radio bursts from neutron stars last fractions of a second to seconds. Flaring stars might produce radio emission for hours. Andy's object was active for weeks at a stretch, which places it in a timescale that very few known objects operate on. The second strange feature is what the team found when they examined the polarization of the signal. Light waves oscillate. Radio waves, like all electromagnetic waves, oscillate in a direction perpendicular to their travel. When waves from many different sources mix together, they oscillate in random directions and cancel each other out. But when something imposes order on that oscillation, the light becomes polarized. It oscillates preferentially in one direction. Andy's object was highly polarized. The degree of polarization was extreme, far higher than most transient radio sources produce. High polarization is associated with strong, ordered magnetic fields. Something in or around the source was organizing the electromagnetic field of the outgoing waves with unusual efficiency. The third strange feature was the invisibility. When astronomers aimed X-ray telescopes and infrared telescopes at the same location during an active phase, they detected nothing. Andy's object existed only in radio wavelengths. For comparison, nearly every known class of energetic cosmic object produces emission across multiple wavelengths. Flaring stars produce X-rays. Magnetars produce X-rays and sometimes visible light. Pulsars produce radio, X-ray, and sometimes visible light. An object that is powerful enough to produce weeks of bright radio emission but completely invisible in every other wavelength is not easily explained by any standard model. Scientists went through the catalogue. Magnetar? The timing was wrong, and the X-ray absence was a serious problem. Low-mass flare star with extreme magnetic activity? The polarization and duration did not fit. Binary star system? No known type of binary produces this exact behavior. An entirely new class of object was on the table. The source sat in a region of space where the magnetic environment is already extreme, and the more researchers examined the galactic center's magnetic structure, the more they realized it was doing things that science had not fully accounted for. Something deep in the core is generating fields and forces that produce behavior outside the textbooks. And those fields are not just affecting radio signals. Every object in space has a signature. Scientists have spent decades building a reference library of those signatures. A pulsar looks like a specific repeating pattern. A flare star produces a certain kind of burst. A magnetar announces itself with a specific combination of X-rays, radio waves, and timing. The library is vast. When a new signal appears, astronomers flip through it and find the closest match. Andy's object does not appear in the library. The team that discovered it published their analysis and invited the wider community to offer explanations. Proposals came in quickly. The scientific community takes unusual signals seriously, especially from the Galactic Center, so researchers from multiple institutions examined the data. The first wave of proposals focused on known exotic objects. Magnetars were the early favorite. They are the most magnetically extreme objects in the known universe. Neutron stars with magnetic fields so intense they can physically distort the shape of atomic nuclei. Magnetars produce bursts of radio waves and X-rays. Their emission can be irregular. Some magnetars have been observed switching on and off over periods of days to weeks. The problem was the X-ray silence. Magnetars always produce X-rays when they are active. Andy's object produced none that any telescope could detect. Researchers ran calculations to see if the geometry of the source or the density of the intervening dust and plasma between Earth and the galactic center could explain the X-ray absence. The numbers were strained. Hiding that much X-ray emission would require an unusual combination of factors that seemed unlikely to align coincidentally. The second wave of proposals involved a class of objects called galactic center radio transients, the same category of intermittent signals first logged in the early 2000s. Andy's object shared some properties with those earlier detections, specifically the location and the general pattern of appearing and disappearing. But the earlier signals were shorter-lived, less polarized, and their properties were less precisely measured because the instruments that found them were less sensitive than the Australian array that found Andy's object. Whether Andy's object belongs to the same family as those earlier transients or represents something different entirely is an open question. If it belongs to the same family, it might be an extreme example of a class that is still being defined. If it is something separate, then the galactic center is producing at least two categories of unexplained transient radio sources simultaneously. A third group of researchers proposed a low-mass star with an unusually intense magnetic field and an extreme flaring cycle. Some small, dim stars are known to produce radio emission during magnetic flares. A few rare examples are highly polarized. But the duration and disappearance pattern of Andy's object did not comfortably fit even the most extreme known examples of stellar radio flares. The complete radio-only behavior remained the sharpest edge of the mystery. An object that generates that much organized electromagnetic energy but produces no corresponding signal in any other wavelength requires a production mechanism that channels almost all of its energy into radio waves alone. Theorists have proposed configurations of rotating plasma trapped in extreme magnetic field geometries that could, in principle, produce this. But those are theoretical constructs, not observed phenomena. What makes Andy's object particularly important is not just that scientists cannot explain it, it is that it sits in the same region as the gamma-ray excess, the unexplained radio transients from the early 2000s, and Sagittarius A star itself. The galactic center is not producing one mystery, it is producing a stack of them, each in a different wavelength, each resisting a different set of explanations, and all of them point to something happening in the magnetic structure of the core that science has not fully mapped yet. Light travels as a wave. Picture a rope stretched between two people. If one person shakes the rope up and down, the wave moves forward while oscillating vertically. If they shake it side to side, the wave oscillates horizontally. Light works the same way. It is an electromagnetic wave that oscillates in a direction perpendicular to its travel. Ordinary light from a light bulb, a campfire, or the sun oscillates in every direction at once. Shake that rope randomly in all directions simultaneously, and you get unpolarized light, millions of waves from millions of atoms, each oscillating in its own random direction, all mixed together. Polarized light is different. Something has imposed order. The waves are oscillating preferentially in one direction, or rotating in a consistent corkscrew pattern as they travel. When you wear polarized sunglasses on a bright day, the lenses block light oscillating in the horizontal direction, which is the dominant polarization of light reflected off flat surfaces like roads and water. That is why the glare disappears. In space, polarization is produced by ordered magnetic fields. When charged particles, like electrons, spiral along magnetic field lines, they produce polarized radio waves. The stronger and more organized the magnetic field, the higher the degree of polarization in the emitted waves. Andy's object was polarized at a level that surprised researchers. The fraction of its radio emission that was polarized was far higher than typical radio sources near the galactic center, where the turbulent environment tends to scramble polarization. Something was generating and sustaining a highly organized magnetic field around or within the source, despite sitting in one of the most magnetically chaotic regions of the galaxy. The galactic center magnetic environment is already extreme. The region closest to Sagittarius A star has a magnetic field thousands of times stronger than the typical magnetic field found in the outer parts of the Milky Way. Long filaments of magnetized plasma, stretch for dozens of light years, aligned parallel to each other in structures called galactic center, non-thermal filaments. These structures have been photographed in radio wavelengths, revealing a magnetic skeleton threading through the central region. Andy's object sat near these structures. Whether it was interacting with them, powered by them, or simply a product of the same extreme magnetic environment is unknown. But the high polarization told astronomers something precise. Whatever process was generating the radio waves had access to strong, ordered magnetic energy, and it was converting that energy into radio waves with exceptional efficiency. The polarization also carries information about what the signal passed through on its journey from the source to Earth. As polarized radio waves travel through plasma, the magnetic field of the plasma rotates their polarization direction. By measuring how much the polarization has rotated, astronomers can estimate the density of the magnetized plasma between Earth and the source. This measurement is called Faraday rotation, named after the 19th century physicist Michael Faraday. The Faraday rotation measured for Andy's object placed it deep inside the galaxy, consistent with its location near the galactic center. The signal had passed through an enormous column of dense, magnetized plasma on its way to Earth. That journey through extreme magnetic environments may itself have shaped some of the signal's properties. The magnetic structure of the galactic center is not just a backdrop to these mysteries, it is actively participating in producing them, and the magnetic energy feeding into the region has a source that occasionally shows its power by venting material on a scale that dwarfs anything in the outer galaxy. Above and below the galactic center, something has punched two enormous tunnels of superheated gas straight through the heart of the Milky Way. These structures stretch for hundreds of light years in both directions. The gas inside them has been heated to temperatures of millions of degrees, and they are venting material out of the galactic core and into the wider galaxy at a continuous, relentless rate. Astronomers call them galactic center chimneys, and they represent one of the clearest signs yet that the sleeping giant at the center of our galaxy is far from truly dormant. The chimneys were mapped using the Chandra X-ray Observatory, a space telescope launched in 1999 that detects X-ray light produced by extremely hot gas. Gas heated to millions of degrees glows in X-rays, the same way a metal rod heated to ordinary temperatures glows red. The hotter the gas, the higher the energy of the light it produces. Chandra can trace the shape of hot gas structures across vast distances with remarkable precision. What the maps revealed was a pair of roughly cylindrical structures, each oriented perpendicular to the flat disk of the galaxy. One pointing up, one pointing down, they connect the chaotic environment of the central molecular zone, the ring of giant gas clouds surrounding Sagittarius A star, to a pair of enormous bubble structures discovered earlier that extend far above and below the galactic plane. Those larger bubbles, known as the Fermi bubbles because the Fermi telescope detected them in gamma rays, extend roughly 25,000 light-years above and below the galactic disk. They are enormous, and the chimneys appear to be the channel through which material from the galactic center feeds into those bubbles, acting as a plumbing system connecting the violent core to the vast structures it has inflated over millions of years. The gas inside the chimneys is moving. It flows outward from the center along the chimney walls, carrying energy and material away from Sagittarius A star and toward the bubbles above and below. The flow rate suggests that the central black hole, despite appearing quiet by the standards of active galactic nuclei in distant galaxies, has been releasing enough energy over time to drive this continuous outflow. That energy release comes in episodes. Sagittarius A star does not feed continuously. It is a quiet black hole most of the time, accreting only tiny amounts of gas and dust from its surroundings. But occasionally, something larger wanders into range, and when it does, the energy release is sudden, violent, and enormous. The chimneys record those episodes. The temperature distribution of the gas inside them, along with the chemical composition and the velocity of the outflow, carries information about the history of past feeding events. Astronomers are reading those records like geological layers in stone, trying to reconstruct a timeline of when Sagittarius A star was last truly active. The evidence points to a major energy release event, somewhere in the range of a few million years ago, possibly linked to a period when the black hole was consuming material at a far higher rate than today. The chimneys may be the aftermath of that episode, still venting material from an ancient explosion that has not yet finished propagating outward. But how does a star get close enough to feed a black hole in the first place? The answer involves one of the most violent events in astronomy, and it happens on a timeline measured not in millions of years, but in individual cosmic moments. Every 20,000 years or so, a star makes a fatal mistake. It wanders too close to Sagittarius A star. The encounter lasts only hours. The star does not survive it. The event is called a tidal disruption event, and it is one of the most energetic single occurrences in the observable universe. Understanding how it works requires understanding something about gravity that seems simple but carries terrifying implications when scaled up to the mass of 4 million suns. Gravity pulls harder on objects that are closer. This is basic physics. But when the gravity source is enormously massive, that difference in pull across a relatively small distance becomes immense. Imagine standing on the side of a cliff. Gravity pulls your feet downward slightly harder than it pulls your head, because your feet are a little closer to Earth's center. That difference across the height of your body is tiny, far too small to feel. Now replace Earth with a black hole 4 million times the mass of the Sunday. The difference in gravitational pull across the length of your body would be enough to stretch you like taffy. This stretching force is called tidal force, named after the same mechanism that makes ocean tides on Earth, where the moon pulls the near side of Earth's oceans slightly harder than the far side. On Earth, the effect is gentle. Near Sagittarius A star, it is lethal. A star approaching the black hole along a path that brings it within a certain critical distance, called the tidal radius, begins to feel tidal forces strong enough to overcome the star's own gravity. The star's self-gravity is what holds it together. When the tidal force from the black hole exceeds the star's own gravitational binding, the star cannot hold itself in a ball anymore. It begins to stretch. The stretching starts slowly as the star approaches. Then, it accelerates. The side of the star nearest the black hole feels a stronger gravitational pull than the side facing away. The star elongates along the direction of travel, stretching into an oval shape, then an elongated egg shape, then a long stream. Scientists who model these events describe the shape the star takes in its final moments as a noodle. The process even has an informal name: spaghettification. At the moment of maximum stretch, the star is no longer a star at all. It is a long, glowing strand of plasma stretching across millions of miles of space, curving around the black hole in a tight arc. The inner part of the strand, caught closer to the black hole, falls inward. The outer part, moving faster and farther out, may escape entirely and spray outward into space. The infalling material does not go straight into the black hole. It forms a swirling disk called an accretion disk, a ring of gas and plasma spiraling inward while heating up through friction and compression. The accretion disk can reach temperatures of millions of degrees. It glows in ultraviolet light and X-rays. A sudden feeding event this large produces a flare of radiation bright enough to outshine the entire galaxy's normal output for weeks or months. Tidal disruption events have been observed in other galaxies, where astronomers watch a previously quiet galactic nucleus suddenly brighten, peak, and then fade over months. Every one of those observed events is a star dying. Every one of them floods the surrounding region with energy, driving gas outward, heating the environment, and leaving behind material that eventually flows up through structures like the galactic chimneys. One of those events happened in our own galaxy's recent past. The evidence is carved into the gas above and below the galactic center, and after the feast, something else happened to the material that escaped the shredding. In the last moments of a tidal disruption event, the star ceases to exist as a coherent object. What remains is a stream of plasma, the fourth state of matter, a gas so hot that electrons are stripped completely from their atoms, leaving behind a mix of free electrons and bare atomic nuclei glowing at millions of degrees. This stream stretches across a distance that can exceed the original diameter of the star by a factor of thousands. The word plasma gets used in everyday life to describe the gas inside a television screen or a fluorescent bulb. The plasma inside a disrupted star is nothing like that. It carries the energy of an entire stellar interior, the fusion fuel of a star, released all at once into a single elongated stream orbiting a supermassive black hole. The plasma in that stream is hotter than the core of most living stars. The dynamics of what happens next are complex and still partly unresolved in astrophysics. The stream of plasma does not simply fall straight into the black hole. The geometry of the disruption and the extreme gravity of the black hole causes the stream to wrap around and intersect itself. When different parts of the stream collide with each other at high velocities, the collisions generate shock waves. Those shock waves heat the gas further and cause parts of the stream to spread out, forming the swirling disk that feeds the black hole. The fraction of the original star's mass that actually falls into the black hole varies depending on the specifics of each event. Roughly half of the disrupted stellar material falls inward in most models. The other half gets ejected. The ejected material moves outward at high speed, eventually joining the surrounding gas and contributing to structures like the galactic chimneys and the Fermi bubbles above and below the galactic plane. In the months following a tidal disruption event, the black hole feeds on the infalling material at a rate far above its usual diet of sparse gas and dust. The accretion disk radiates intensely. Observations of tidal disruption events in other galaxies show the nucleus of the host galaxy brightening by factors of hundreds or even thousands over its normal output, then slowly fading as the supply of stellar material is consumed. For Sagittarius A star, tidal disruption events happen roughly once every 20,000 years. On human timescales, that seems rare. On cosmic timescales, it is frequent enough that the cumulative energy released over the galaxy's lifetime has shaped the large-scale structure of gas around the core. Each event adds to the outflow. Each event pumps more material into the chimneys. Each event leaves its signature in the chemical composition and temperature distribution of the gas surrounding the black hole. Scientists studying the Fermi bubbles and the galactic chimneys found evidence that one particularly energetic episode occurred a few million years ago, possibly involving either a single large tidal disruption event or a period of elevated accretion from a gas cloud that fell into the black hole's vicinity. The energy released during that episode was large enough to have inflated the bubbles to their current enormous size. The plasma from that ancient feeding event is still moving, still flowing outward along the chimneys, still heating the gas above and below the galactic plane. The star that triggered it is long gone, stretched and swallowed, but the ripple it sent through the galaxy is still propagating, still visible to instruments, sensitive enough to trace its edges, still reshaping the environment of our home galaxy from the inside out. And the story of what the black hole does with ejected material from those events, and how it hurls entire stars out of the galaxy altogether, is where the scale of the galactic center's violence becomes truly impossible to ignore. When Sagittarius A star tears apart a star and swallows half of it, the energy released does not stay local. It cannot. The violence of a tidal disruption event is so extreme that the surrounding environment responds for millions of years afterward. The shock waves from that feeding moment travel outward through the galactic center, heating gas, compressing clouds, and carving structures that astronomers are still measuring today. A shockwave in space works the same way a shockwave works in air. When an explosion occurs, it pushes outward in all directions, compressing the surrounding medium as it goes. The compressed region forms a shell, a bubble of higher pressure moving away from the source. In air, you hear it as a boom. In space, where there is no air to carry sound, the The shockwave moves through gas and plasma, heating everything it contacts and leaving behind a boundary between the shocked and unshocked material. The galactic center is surrounded by the central molecular zone, a ring of giant gas clouds containing some of the densest molecular material in the galaxy. These clouds sit at distances ranging from a few dozen to a few hundred light-years from Sagittarius A star. When a powerful energy release from the black hole sends shockwaves outward, those shockwaves slam into the cloud walls of the central molecular zone. The collisions heat the surface layers of the clouds and compress them, sometimes triggering new star formation inside the clouds. Above and below the central molecular zone, the environment is less dense. Gas and plasma fill the space between the clouds, and when shockwaves reach that region, they can travel much farther before losing energy. That is how the chimneys formed. Repeated energy releases from the galactic center punched shockwaves preferentially through the lower density channels above and below the disk of the galaxy, carving and maintaining the cylindrical structures that Chandra mapped in X-rays. The chimneys are not static tunnels. The gas inside them is in constant motion, driven by the pressure differential between the hot, energetic core and the slightly cooler surrounding gas. Material flows upward and downward along the chimney walls, carrying heat, magnetic field energy, and chemical elements from the galactic center outward into the Fermi bubbles. One of the more striking features that Chandra revealed was a set of sharp edges along the chimney walls. Those edges mark the boundary between the fast, hot gas inside the chimney and the slower, denser gas around it. The sharpness of those edges tells scientists how recently the last major shockwave passed through. A sharp edge means the shockwave was geologically recent. A blurred edge means the boundary has had time to mix and soften. The edges are still sharp. Whatever last drove a powerful shockwave through those chimneys happened recently enough, on cosmic timescales, that the structures have not yet had time to blur and dissipate. The galactic center is still active, still venting, still sending shockwaves through the system. And the material it is launching outward, heated to millions of degrees and accelerated by those shockwaves, eventually reaches the edge of the chimney structures and spills out into the Fermi bubbles above and below the galactic disk. Those bubbles are vast enough to contain our entire solar system tens of millions of times over. They are a monument to the energy output of a black hole that most astronomers classify as quiet, and the shockwaves feeding them are also throwing solid objects outward, objects that started as stars and end up as refugees crossing the entire galaxy at speeds that should be impossible. Most stars spend their entire lives in roughly the same neighborhood. Our Sun has been orbiting the center of the Milky Way for about 4.5 billion years, completing a full loop every 225 million years or so. Stars are not going anywhere fast. They drift, they orbit, they stay put. Some stars do not follow that rule. Hypervelocity stars are objects moving so fast that the gravity of the entire Milky Way cannot hold them. They are on escape trajectories, heading outward from the galactic center and destined to leave our galaxy permanently, traveling through intergalactic space forever. Astronomers have identified dozens of them so far, and every one of them traces its origin back to the central region of our galaxy. The mechanism that produces them involves Sagittarius A star directly. Imagine two stars orbiting each other as a binary pair, a common configuration in the galaxy. Binary pairs travel through the galactic center together, bound to each other gravitationally, approaching the black hole on a close trajectory. As they swing near Sagittarius A star, the gravity of the 4 million solar mass black hole overwhelms the gravitational bond between the two stars. The pair gets separated violently. One star gets captured, falling into a tight orbit around the black hole or being consumed by it. The other star gets slingshot outward at enormous speed. The energy for that slingshot comes from the orbital energy of the binary pair around the black hole. Gravity redistributes that energy with brutal efficiency, flinging one star inward and launching the other outward. The speeds these stars reach are staggering. Some have been measured traveling at over 1,000 miles per second. To put that in context, Earth travels around the Sun at about 18 miles per second. The Milky Way's escape velocity at our position is roughly 350 miles per second. A hypervelocity star moving at over 1,000 miles per second is traveling at nearly 3 times the speed needed to escape our entire galaxy. These stars do not slow down. Once launched, they travel through the galaxy in a nearly straight line, cutting across the curved orbits of normal stars at extreme speed. Astronomers trace their paths backward and find that the trajectories converge on the galactic center. The fingerprints of Sagittarius A star are on every one of them. For a star to reach hypervelocity, the binary disruption has to happen within a very close range of the black hole, the same region where the stars orbit, the same region where the galactic center radio transients originate, the same region where the gamma-ray glow is brightest. The core of the Milky Way is producing hypervelocity stars, unexplained radio signals, gamma-ray excess, and the chimneys all from the same small patch of space. From Earth, a hypervelocity star moving at 1,000 miles per second could travel from here to the Moon in roughly 4 minutes. In cosmic terms, they are bullets, and the gun that fired them is the same object responsible for every other mystery in this story. The stars that get slingshot outward are not the only material escaping the galactic center. Gas, plasma, magnetic fields, and the shockwave energy from ancient feeding events all push material outward. The galactic center is not consuming the galaxy, it is spending it, flinging pieces of it outward at speeds and energies that reshape the structure of the Milky Way from the inside. And deep inside the structures surrounding the black hole, in the dense clouds of gas that orbit the central region, the environment produces something completely unexpected. Not violence, chemistry. Escape velocity is the speed an object needs to break free from a gravitational field without any additional push. On Earth, escape velocity is about 7 miles per second. Fire a rocket at that speed straight up and it will keep going, trading kinetic energy for altitude until it is free of Earth's gravity entirely. Fall short of that speed and gravity wins. The rocket arcs back down. Every gravitational system has an escape velocity. The Moon's is much lower than Earth's, which is why the Apollo missions needed far less fuel for the lunar ascent than for the original launch. Jupiter's is enormous, which is why escaping its atmosphere would require speeds far beyond what any human-made vehicle has ever needed for Earth launch. The Milky Way has an escape velocity too. From our position in the galaxy, about 26,000 light-years from the center, the escape velocity is approximately 340 miles per second. That is the speed something needs to reach to leave our galaxy and travel into the intergalactic void between the Milky Way and its nearest neighbors. Hypervelocity stars exceed that threshold dramatically. Stars moving at 700, 800, or over 1,000 miles per second are traveling at roughly 2 to 3 times galactic escape velocity. They are not borderline cases. They are on trajectories so extreme that even if the Milky Way's gravity could reach out and grab them, it would not be enough. These objects are leaving permanently, irreversibly, on timescales of millions of years. What happens to a star after it escapes the Milky Way is a question with no definitive answer yet, because none of the hypervelocity stars we have tracked has actually reached the edge of the galaxy in the time we have been watching. They are still crossing the galactic disk, still visible to our telescopes, moving fast enough that astronomers can measure their velocities with precision. Astronomers use a technique called spectroscopy to measure how fast objects are moving toward or away from us. When a light source moves away, its light waves stretch out slightly, shifting toward the red end of the spectrum. When it moves toward us, the waves compress, shifting toward the blue end. By measuring how much a star's light has shifted, scientists can calculate its velocity along our line of sight with extraordinary precision. The fastest confirmed hypervelocity stars show Doppler shifts consistent with speeds that place them well above galactic escape velocity. Their trajectories, extrapolated forward in time, carry them beyond the edges of the Milky Way's disk and into intergalactic space within the next tens of millions of years. Once there, they will travel through the dark between galaxies. The intergalactic medium is not completely empty. It contains sparse wisps of ionized gas and magnetic fields threading through the large-scale structure of the universe. But it is as close to empty as space gets. A hypervelocity star crossing that void would encounter almost nothing for billions of years. Whether any planets orbit these stars, and whether those planets could have ever supported life before being violently ejected from the galactic core, is a question scientists have begun to take seriously. A planet orbiting a hypervelocity star would have formed in the chaotic central region of a galaxy, survived the slingshot event, and then spent its existence traveling through a void with no neighboring stars. The galactic center launches these objects constantly, has done so for billions of years. The intergalactic space surrounding the Milky Way may be populated with escaped stars that once orbited close to Sagittarius A star, each one a record of a gravitational interaction that also fed the black hole, heated the chimneys, and contributed to the glow of gamma rays spreading outward from the core. The violence that ejects stars is the same violence that builds the structures around the black hole, and those structures contain surprises that have nothing to do with energy or speed. Pull back from the immediate neighborhood of Sagittarius A star and look at the wider region surrounding the galactic center. At distances ranging from roughly 30 to a few hundred light-years from the black hole sits a ring of massive gas clouds, some of the densest concentrations of molecular material in the entire galaxy. This region is called the Central Molecular Zone, and it is stranger than most people imagine a neighborhood around a supermassive black hole to be. Molecular clouds are regions of space where the gas is cold and dense enough for atoms to bond together into molecules. Hydrogen pairs up into molecular hydrogen. Carbon and oxygen combine into carbon monoxide. Other combinations produce water, ammonia, formaldehyde, and more complex chains of atoms. The galactic center, despite being surrounded by one of the most violent environments in the Milky Way, manages to host these cold molecular clouds in the space between its outflow structures. What astronomers found inside these clouds was not just simple molecules. Radio telescope surveys of the central molecular zone have detected dozens of complex organic compounds, carbon-based molecules that form the chemical building blocks of chemistry as humans understand it. Amino acid precursors, long carbon chains, alcohols. One of the most striking finds is the presence of enormous quantities of ethanol, the same compound found in alcoholic beverages, existing in clouds large enough that if you could somehow collect just the alcohol molecules from a single cloud in the central molecular zone, you would have a quantity that defies any useful comparison. Ethanol does not require life to form. It assembles spontaneously in cold, dense molecular clouds when ultraviolet light from nearby stars drives chemistry on the surface of tiny ice-coated dust grains. The galactic center provides all the necessary ingredients: carbon, oxygen, hydrogen, and ultraviolet radiation in abundance. The chemistry runs on its own, but the presence of complex organic chemistry in the central molecular zone matters for a larger reason. The same types of molecules detected there are the same types found in molecular clouds throughout the galaxy, including the cloud that eventually collapsed to form our solar system 4.5 billion years ago. The chemistry of life's precursors is not rare or exotic. It runs wherever the conditions allow, even in the chaotic environment surrounding a supermassive black hole. The central molecular zone also contains some of the most massive molecular clouds in the galaxy. Some of these clouds weigh millions of times the mass of our Sunday. The famous Sagittarius B2 cloud, one of the largest molecular complexes near the galactic center, is a region of active star formation sitting just over 300 light-years from Sagittarius A star. New stars are forming there right now, inside a molecular cloud that is simultaneously being bathed in X-rays from the black hole's neighborhood and shredded at its edges by the intense ultraviolet radiation from massive young stars nearby. The central molecular zone is a place where star formation, chemical complexity, extreme radiation, and the gravitational influence of a supermassive black hole all operate simultaneously. It is not a simple environment. It is a chemistry lab, a stellar nursery, and a demolition zone all at once, and it sits between Earth and everything else the galactic center is doing. And the energy flowing through this zone from all those sources adds up to something that makes the galactic center the most energetic region in the Milky Way by a significant margin. The outer regions of the Milky Way, where our solar system lives, are, by galactic standards, calm. Stars burn steadily. The interstellar medium between them is thin and cool. Cosmic rays pass through but rarely interact. Our corner of the galaxy produces energy at a rate typical for spiral galaxy disks, distributed evenly among hundreds of billions of stars. The galactic center operates on a completely different scale. Pack the same number of stars into a space thousands of times smaller, add a supermassive black hole pulling on everything within reach. Surround it with molecular clouds being bombarded by X-rays and cosmic rays. Add the shockwaves from ancient feeding events, and the magnetic field lines threading through everything at intensities thousands of times greater than in the outer disk. The energy density of the galactic center, the amount of energy flowing through each cubic light-year of space, dwarfs anything in the region where we live. Astronomers measure energy output from different regions of the galaxy in multiple wavelengths. The galactic center produces intense emission in radio waves, infrared, X-rays, and gamma rays simultaneously. Every one of those wavelengths carries information about a different process operating in the core, and every one of those processes is running at a rate that would be considered extreme anywhere else in the galaxy. The magnetic field alone contributes significantly. Strong magnetic fields store energy. When magnetic field lines reconnect, which happens when fields of opposite orientation meet and snap into new configurations, they release that stored energy in sudden bursts. This process, called magnetic reconnection, powers solar flares on our Sunday. In the galactic center, where the magnetic field is thousands of times stronger, magnetic reconnection events release proportionally more energy. These events accelerate charged particles to near light speed, producing the synchrotron radiation that astronomers detect in radio wavelengths across the central region. The cosmic ray density in the galactic center is also far higher than in the outer disk. Cosmic rays are charged particles, mostly protons, traveling at nearly the speed of light. They are produced by supernova explosions and accelerated by strong magnetic fields. When cosmic rays collide with the dense gas in the central molecular zone clouds, they produce gamma rays through a process called pion decay. This contributes an additional layer of gamma ray emission on top of the excess glow that Fermi detected, making the task of separating different gamma ray sources in the galactic center an extremely complex data analysis problem. The combined output of all these processes makes the galactic center a dominant feature of the galaxy in nearly every wavelength. If you could visualize the Milky Way in X-rays, the center would blaze. In radio waves, it would be the brightest region by far. In gamma rays, the spherical glow of the excess would dominate the view of the entire inner galaxy. All of this energy output is relevant to the mystery of the gamma ray excess because it creates a noisy environment. Separating the excess from all the other gamma ray sources in the core requires accounting for every known contributor with precision. Any error in that accounting produces a false residual. Critics of both the dark matter and pulsar theories argue that the excess itself might be partly or entirely an artifact of imperfect background subtraction. That possibility has not gone away. But it has not killed either theory either, because independent lines of evidence keep pointing back to something real in the data. And one of those lines of evidence involves a very specific energy signature that dark matter physics predicted before the Fermi telescope even launched. In physics, a prediction is only as powerful as its specificity. Saying a phenomenon will produce some form of radiation somewhere in the electromagnetic spectrum is a weak prediction. saying it will produce radiation at a very specific energy level from a specific region of space with a specific spatial distribution, is a strong prediction. Strong predictions are how science advances. Decades before the Fermi telescope detected the galactic center gamma-ray excess, theorists working on dark matter models made a specific prediction. If dark matter particles are their own antiparticle, meaning each particle can annihilate with another particle of the same type, and if they can enter an excited energy state before annihilating, the annihilation produces gamma rays at a well-defined energy level. The energy level, predicted by a class of models involving excited dark matter, states corresponds to 511 kiloelectron volts per photon. 511 kiloelectron volts is also the energy released when an ordinary electron meets its antimatter counterpart, a positron, and they annihilate each other. This same energy signature shows up in medical positron emission tomography scans, where radioactive tracers release positrons that annihilate with electrons in body tissue, producing 511 kiloelectron volt photons that the scanner detects. The galactic center has been known for years to produce a diffuse glow of 511 kiloelectron volt photons. The source of those positrons in the central region has long been debated. Radioactive elements produced by supernovae decay and release positrons. Cosmic ray interactions produce them. Millisecond pulsars are also known positron sources, but the spatial distribution of the 511 kiloelectron volt emission from the galactic center does not perfectly match the distribution of any of those known sources alone. The emission is concentrated toward the center in a way that hints at something more fundamental, producing it, something that concentrates where the gravitational potential is deepest, which is exactly where dark matter should concentrate. This is where the excited dark matter models enter. Some theoretical frameworks propose that dark matter particles can absorb energy from collisions and enter a slightly higher energy state, then release that energy and drop back to their ground state, producing photons in the process. The specific energy of those photons depends on the mass difference between the excited and ground state of the dark matter particle. For a set of models published years before current observations, the predicted photon energy falls precisely in the range that produces the 511 kiloelectron volt signal. The match between prediction and observation does not prove dark matter is the source. Known processes also produce this emission, but the match is specific enough to be taken seriously, and it is independent of the broader gamma-ray excess argument, providing a second potential signal from a second independent measurement. In 2026, a research team published results linking the 511 kiloelectron volt emission, the galactic center gamma-ray excess, and a third unexplained signal in the X-ray band to a single, coherent, excited dark matter model. All three signals, measured independently, at different energies, by different instruments, fit the predictions of the same dark matter model without requiring any adjustments to the parameters. 3 independent signals, 1 prediction. The team called it the strongest multi-messenger case for dark matter ever assembled. Critics called for more data and independent verification. The debate is ongoing, but no one in the field is dismissing it anymore. And sitting alongside these energy arguments is a theory so radical it reframes the entire question of what Sagittarius A star actually is. Science rarely delivers clean moments. Most breakthroughs arrive as slow accumulations, one paper building on another, each one nudging the probability a little further in one direction. The kind of moment where multiple independent measurements suddenly align behind a single explanation is rare. When it happens, the field stops arguing for a moment and pays attention. 2026 produced one of those moments for galactic center research. A research team working with data from multiple space observatories published an analysis connecting 3 separate anomalous signals from the galactic center to a single theoretical framework. Each signal had been known for years. Each had its own literature, its own competing explanations, its own unresolved debates. No one had previously shown that all 3 could be explained simultaneously by one model without adjusting the parameters to fit each signal individually. The first signal was the gamma-ray excess, the massive spherical glow detected by the Fermi telescope, centered on the galactic center and spreading 5,000 light-years outward. The second was the 511 kiloelectron-volt positron annihilation signal, the concentrated glow of a specific energy photon coming from the central bulge of the galaxy. The third was an anomalous X-ray emission line detected in the inner galaxy by a separate orbital observatory, which had resisted clean explanation for several years. The team applied an excited dark matter model. In this model, dark matter particles exist in two states, a lower energy ground state and a slightly higher energy excited state. When two dark matter particles collide, one can transfer energy to the other, knocking it into the excited state. The excited particle then decays back to its ground state, releasing the energy difference as a photon. The energy of that photon depends on the mass difference between the two states. When the team ran the numbers for their specific model, the photon energies from excited dark matter decay match the 511 kiloelectron-volt signal and the anomalous X-ray line. The rate at which those collisions would occur in a dark matter cloud concentrated around Sagittarius A star matched the overall brightness of both signals, and the spatial distribution of collisions in a dark matter halo following the expected density profile matched the shape of the gamma-ray excess. All three signals, one model, no parameter tuning between signals. The team was careful in how they presented the results. They acknowledged that each individual signal had alternative explanations. They were clear that the alignment between prediction and observation did not constitute proof. They called for follow-up observations from future instruments to test specific additional predictions that their model made. But the paper drew significant attention because multi-signal alignments of this kind are extremely rare in high-energy astrophysics. Getting one signal to fit a model is achievable by adjusting parameters. Getting three independent signals measured at different energies by different instruments to fit the same model simultaneously with no additional adjustment is a meaningful result. The pulsar camp responded that millisecond pulsars are known to produce positrons and contribute to the 511 kiloelectron-volt emission, and that a large enough undiscovered pulsar population could in principle produce all three signals through ordinary physics without invoking dark matter. The response was acknowledged but noted to require a pulsar population with very specific properties that have not been observed elsewhere in the galaxy. The field is watching, new data is coming, and in parallel with this debate, a more fundamental question has quietly gathered support among a small group of theorists. A question about whether Sagittarius A star is actually what everyone assumes it to be. For decades, Sagittarius A star has been called a supermassive black hole. The evidence for that classification is strong. Stars orbit it. Their orbits imply a mass of 4 million suns concentrated in a region smaller than our solar system. The gravity is so intense that nothing we observe nearby escapes it. When the Event Horizon Telescope published the first direct image of the region around Sagittarius A star in 2022, the image showed a ring of glowing gas surrounding a dark central region, matching what general relativity predicts for a black hole of that mass. But a small group of physicists has been asking a quiet question for years. What if the object at the center is not a black hole in the traditional sense, but rather an ultra-dense concentration of dark matter particles, so tightly packed that it mimics the gravitational behavior of a black hole from the outside? The idea is called a dark matter boson star, or in some formulations, a dark matter soliton. These are theoretical objects that arise in models where dark matter is a very light particle called an ultralight axion. Ultralight axions are an alternative dark matter candidate to the heavier, weakly interacting massive particles. They are so light that quantum mechanical effects become important on large scales, causing the dark matter to behave more like a wave than a collection of individual particles. In galaxy halos, ultralight axion dark matter forms a smooth, spread-out distribution. At the center of a galaxy, where the gravitational potential is deepest, the wave-like dark matter condenses into a soliton, a stable, self-sustaining concentration of dark matter that can persist indefinitely without collapsing into a singularity. A massive enough soliton could produce a gravitational field from the outside that looks identical to a black hole of the same mass. Stars orbiting it would trace the same elliptical paths. The bending of light around it would match black hole predictions. The radio emission from gas falling into it would look similar to accretion disk emission from a black hole. The difference, in theory, shows up at the boundary. A black hole has an event horizon. Once something crosses it, it cannot return. A dark matter soliton has no event horizon. Matter falling toward the center would slow, interact with the dense dark matter medium, and potentially be reflected or absorbed without a point of no return. If Sagittarius A star is a soliton, the nature of the galactic center emission changes significantly. The gamma-ray glow could arise from dark matter annihilation inside the dense soliton core, rather than from particle collisions in a surrounding halo. The specific energy signatures detected would reflect the properties of the ultralight axion rather than a heavier, weakly interacting massive particle. And the behavior of objects, like Andy's object, sitting in the electromagnetic environment near a soliton rather than a traditional black hole, might differ in subtle but measurable ways. The Event Horizon Telescope image does not definitively rule out this possibility. A sufficiently dense soliton can produce a shadow in radio wavelengths that matches the predicted black hole shadow closely enough that current instruments cannot distinguish between them. Testing this theory requires observations at higher resolution or detecting some physical signature that differs between the two models. Several research teams are working on identifying those signatures. The answers, if they arrive, will come from instruments not yet fully operational. Meanwhile, the instrument that first identified Andy's object is part of a larger network being constructed that may provide exactly the kind of data needed to push this debate forward. Stand back for a moment and consider the weight of what that question carries. The supermassive black hole at the center of the Milky Way is one of the most studied objects in modern astronomy. Decades of observations, multiple Nobel Prize-winning research programs, the first direct image of its shadow. If Sagittarius A star turns out to be a dark matter soliton instead of a traditional black hole, the implications extend far beyond our galaxy. Every large galaxy observed so far appears to have a supermassive object at its center. The relationships between those objects and their host galaxies are among the most reliable scaling laws in astrophysics. The mass of the central object correlates with the mass of the galaxy's central bulge. It correlates with the speed of stars in that bulge. Astrophysicists use these relationships to estimate the properties of distant galaxies from measurements of their central objects. If at least some of those central objects are dark matter solitons rather than black holes, those scaling relationships would need to be reinterpreted. The processes that form and grow these objects over cosmic time would need new models. The history of how galaxies evolved over billions of years, which depends heavily on the feedback effects of supermassive black holes, would need revision. The distinction also matters for gravitational wave astronomy. When two black holes merge, they produce gravitational waves, ripples in the fabric of space-time that spread outward at the speed of light. The Laser Interferometer Gravitational Wave Observatory and similar facilities have detected dozens of black hole mergers. When supermassive black holes in the centers of merging galaxies eventually come together, they should produce gravitational waves at lower frequencies than stellar mass black hole mergers. The Pulsar Timing Array, a network of precisely timed pulsars used as a gravitational wave detector, has found hints of this background signal. If some galactic center objects are solitons, their mergers would produce gravitational wave signatures distinct from black hole mergers. The signal might be broader or have a different frequency structure. Future space-based gravitational wave detectors, planned for launch in the coming decades, may be sensitive enough to distinguish between the two. More immediately, the Soliton model makes predictions about the behavior of objects orbiting very close to Sagittarius A star. Stars in the S cluster, orbiting within a few light hours of the center, should behave identically around a black hole and a soliton of the same mass at the distances currently observed. But at closer ranges, the models diverge. A soliton has a finite density even at its center. A black hole becomes infinitely dense at its singularity. Objects that pass through the outer layers of a soliton experience different gravitational effects than objects approaching a black hole event horizon. Future telescopes with higher angular resolution may track the orbits of stars or gas clouds close enough to the center to detect those differences. The next generation of extremely large ground-based optical telescopes, currently under construction in Chile and Hawaii, will sharpen our view of the galactic center to the point where individual stellar orbits can be measured with far greater precision than today. Whatever Sagittarius A star turns out to be, the answer will come from better instruments. And the instrument that found Andy's object is part of a growing network that is already rewriting what we know about the galactic center in radio wavelengths. In the flat, dry outback of Western Australia, far from any city lights or radio interference, a field of white dish antennas sits beneath an enormous sky. 36 dishes, each 12 meters across, spread across an area roughly 3 miles wide. Individually, each dish is a modest instrument. Together, working in coordination, they function as a single radio telescope with effective collecting power far greater than any individual dish could achieve. This is the Australian Square Kilometre Array Pathfinder, the instrument that found Andy's object. It is not just a telescope. It is a prototype and proving ground for the Square Kilometre Array, the most ambitious radio telescope project in human history, currently under construction across both Australia and South Africa. The design philosophy behind the Pathfinder is survey speed. Traditional large radio telescopes, like the famous Arecibo dish in Puerto Rico, could point at one patch of sky at a time with great sensitivity. The Pathfinder uses a technology called phased array feeds, which allow each dish to observe multiple patches of sky simultaneously. Instead of a single narrow field of view, each dish captures a wide field, and the 36 dishes working together can survey enormous areas of sky in a fraction of the time older instruments required. That speed is what made finding Andy's object possible. A transient source that appears for weeks and then disappears would be easy to miss with a telescope that only revisits each patch of sky occasionally. The Pathfinder's rapid survey cadence caught the source appearing and disappearing multiple times, providing enough observations to characterize its behavior and confirm it was real. The data from the Pathfinder arrives as an enormous stream of numbers. Processing it requires automated systems that flag unusual signals for human review. When Andy's object appeared in the survey data, automated algorithms identified it as a statistical outlier. A researcher reviewing the flagged sources noticed its properties and recognized that it did not match any standard classification. The Pathfinder has since found additional radio transient sources in and around the galactic center. Some share characteristics with Andy's object, others appear distinct. The growing catalogue of galactic center radio transients is building a picture of a population of objects or behaviors that existing models did not predict. The full square kilometre array will be roughly 50 times more sensitive than the Pathfinder, covering a much larger area with far more collecting power. When fully operational, it will survey the entire sky visible from its southern hemisphere location every few days. Every transient source that appears and disappears over days, weeks, or months will be caught, characterized, and added to a catalogue that will transform our understanding of dynamic phenomena in the universe. For galactic center research specifically, the Square Kilometre Array will detect radio emission from individual millisecond pulsars in the central region that current instruments cannot resolve. If the pulsar army theory is correct, the array will find it. If pulsars cannot account for the observed emission on their own, the data will sharpen the case for the alternative explanation. It will also monitor Andy's object and its relatives continuously, tracking their appearance and disappearance cycles, measuring their polarization, evolution, and searching for any correlated behavior in other wavelengths by coordinating with space telescopes operating simultaneously. The instrument that changed the field was a prototype. The one being built now will be an order of magnitude more powerful, and even before it is complete, ground-based and space-based observatories are pointing at the Galactic Center with capabilities that previous generations of astronomers could only imagine. The universe contains two broad categories of objects. Persistent sources produce radiation continuously and predictably over timescales far longer than any human observation program. Stars, galaxies, nebulae, and most pulsars fall into this category. Transient sources appear suddenly, change dramatically, and often disappear. Supernovae, gamma-ray bursts, and certain types of flaring stars fall into this category. The distinction matters because transients are the universe's way of showing you an event rather than a state. A persistent source tells you what an object looks like when it is in equilibrium. A transient source shows you what happens when something changes violently and quickly. The Galactic Center is producing transients in numbers and with properties that challenge existing frameworks for how these events work. Gamma-ray bursts are the most energetic transients in the universe. A gamma-ray burst releases more energy in seconds than our Sun will release in its entire 10 billion-year lifetime. They are detected from across the observable universe, billions of light-years away. They are caused by specific violent events, either the collapse of a rapidly spinning massive star or the merger of two neutron stars. The Galactic Center transients documented over the past 2 decades share some properties with gamma-ray bursts, but differ in fundamental ways. The timescales are far longer, lasting hours, days, or weeks rather than seconds. The energy output is far lower, and the location, concentrated near the Galactic Center, rather than distributed randomly across the sky, suggests the source population is tied to the unique environment of the galactic core. Radio transients, as a class, were once considered rare and exotic. In the past decade, advances in survey technology have revealed them to be far more common than previously assumed. Fast radio bursts, a class of intense millisecond duration radio pulses now known to originate from distant galaxies, were completely unknown before 2007. In just a few years, hundreds of them have been detected, and a subset have been traced to magnetars. Their discovery required instruments with the same kind of rapid survey capability that found Andy's object. The Galactic Center transients may represent a similarly significant population of objects waiting to be properly catalogued and understood. The properties of the known examples suggest they are distinct from fast radio bursts. They are slower, more polarized, and confined to the Galactic Center region, but the principle is the same. A class of object that was effectively invisible to older instruments, revealed by newer ones capable of scanning larger areas more frequently. Understanding transients requires catching them in the act. A source that is only active for a few weeks out of every few months presents a specific observational challenge. You need an instrument that covers enough sky, with enough sensitivity, and at a high enough cadence to catch the source during its active phase and follow it through its disappearance. The more sources you catch, the more you can study the distribution of their properties, which is how scientists distinguish between different physical origins. The Galactic Center transient population is growing. Each new example adds a data point. Scientists are beginning to see patterns in the timescales, polarization levels, and energy outputs of these sources. Whether those patterns will eventually converge on a single explanation or reveal multiple distinct populations is a question the next generation of instruments is already starting to answer. And those instruments are not just looking in radio wavelengths. They are scanning simultaneously across the entire electromagnetic spectrum, trying to catch the moment when one of these mysterious sources illuminates in one wavelength but stays dark in others, which itself carries information about the physics of the source. The gas flowing through the galactic chimneys mapped by the Chandra Observatory is not merely hot by human standards, it is hot by stellar standards. The temperature inside those chimney structures reaches tens of millions of degrees Fahrenheit, comparable to the interior temperature of a mid-sized star. Gas at those temperatures does not produce visible light. It produces X-rays, and those X-rays are what Chandra detected, allowing astronomers to trace the chimney structures with remarkable precision. To produce gas at tens of millions of degrees, you need a source of energy capable of heating material with extraordinary efficiency. The primary mechanism inside the galactic chimneys is a combination of two processes. The first is direct energy injection from shockwaves originating at the galactic center. Shockwaves compress and heat the gas they pass through. The stronger the shockwave, the higher the temperature it produces. Shockwaves from tidal disruption events and from magnetic reconnection episodes near Sagittarius, a star, propagate outward through the lower density gas above and below the galactic disk, pumping energy into the chimney material continuously. The second process is viscous heating. As hot gas flows through the chimneys, different layers move at slightly different speeds. The friction between these layers converts kinetic energy into heat, similar to the way rubbing your hands together generates warmth. On the scale of gas flowing through structures hundreds of light years long, that friction operates continuously and adds meaningfully to the overall temperature of the chimney gas. The chemical composition of the chimney gas carries its own information. Hot gas at millions of degrees strips electrons from atoms, producing a plasma of ions. Different elements lose their electrons at different temperatures, so the mix of ions detected in the chimney plasma tells astronomers how hot the gas has been at different points in its journey from the galactic center to the outer edges of the chimneys. By mapping the temperature distribution along the chimney length, scientists reconstruct the history of energy injection events that produced them. One surprising finding from the Chandra maps was the presence of relatively cool gas filaments threading through the hotter chimney material. These cool filaments should not survive in an environment heated to millions of degrees. The hot surrounding gas should evaporate them rapidly. Their persistence suggests that magnetic fields are playing a protective role, insulating the cool gas from the surrounding heat and allowing it to survive inside the chimney structure far longer than thermal physics alone would predict. This magnetic insulation is a known phenomenon in smaller astrophysical systems. In the solar corona, the atmosphere of our own sun, magnetic fields confine and structure hot plasma loops, creating the temperature inversion, where the sun's atmosphere is millions of degrees hotter than its surface. The galactic chimneys appear to operate on the same principle at a vastly larger scale. The temperature of the chimney gas also determines how fast it flows. Hot, pressurized gas moves outward faster than cooler gas under the same pressure gradient. Measurements of the flow velocity inside the chimneys show the gas moving at speeds consistent with the estimated energy input from the galactic center. The energy budget closes. The heating mechanisms account for the temperature. The temperature accounts for the flow speed. The flow speed accounts for the rate at which material reaches the Fermi bubbles above and below the galactic disk. All of it connects. The chimneys are not isolated structures. They are the visible trace of an energy transport system carrying the output of the galactic center outward through the galaxy. And that output is reshaping things far beyond the immediate neighborhood of Sagittarius A star. The energy leaving the galactic center through the chimneys and Fermi bubbles does not simply dissipate into empty space. It interacts with everything it encounters. Gas clouds, cosmic rays, magnetic fields, and the sparse interstellar medium all feel the influence of energy injected from the core. Over billions of years, this influence has contributed to shaping the chemical composition of the gas throughout the Milky Way, including the gas that eventually collapsed to form our Sun and the planets orbiting it. Cosmic rays are one of the primary carriers of galactic center energy into the wider galaxy. Cosmic rays accelerated by shockwaves near Sagittarius A star travel outward at close to the speed of light, threading through the galaxy's magnetic field along paths that spiral and curve. When they collide with atoms in interstellar gas clouds, they ionize those atoms, stripping electrons and creating charged ions. Ionized gas is chemically reactive in ways that neutral gas is not. Reactions that would not occur in neutral gas proceed rapidly when the gas is ionized. This ionization chemistry is partly responsible for the rich molecular diversity found in interstellar gas clouds throughout the galaxy. Complex molecules, like those detected in the central molecular zone, also appear in molecular clouds far from the galactic center. The same chemistry runs wherever cosmic rays penetrate, driven in part by the energetic particles accelerated at the galactic center and spreading outward over millions of years. The Fermi bubbles themselves are thought to be inflated partly with cosmic rays produced near the galactic center. The edges of the bubbles, detected in radio waves and gamma rays, show the signature of energetic electrons spiraling in magnetic fields and emitting synchrotron radiation. Those electrons were accelerated somewhere near the core and carried outward by the expanding bubble walls. As the bubbles grow, they carry this population of energetic particles into the galactic halo, the diffuse region above and below the galactic disk that surrounds the main stellar body of the Milky Way. The galactic halo is not empty. It contains a diffuse warm plasma and magnetic fields that extend far beyond the visible disk of stars. Cosmic rays entering the halo from the Fermi bubbles affect the pressure balance of that plasma, contributing to a galactic wind that slowly pushes material from the galaxy's disk out into the halo and beyond. Some of that material eventually falls back in, carrying enriched chemistry. Some escapes entirely. Heavy elements, produced by supernovae near the galactic center and throughout the disk, get mixed into this recycled material. When it falls back onto the disk, it seeds new generations of gas clouds with the chemical building blocks of future stars and planets. The galactic center's energy output is part of the mixing engine that distributes the chemistry of stellar nucleosynthesis across the galaxy. Our solar system formed from a gas cloud that had been through multiple cycles of this mixing. The iron in your blood was forged in a supernova, possibly many of them, whose remnants were mixed into the interstellar medium by processes partly driven by the energy output of the galactic center. The carbon in your cells was produced in the cores of old stars and scattered by stellar winds. The water on Earth assembled from hydrogen and oxygen that cycled through interstellar chemistry, driven partly by cosmic rays with origins in the galactic core. The galactic center is not a remote and disconnected place. Its energy output has been touching the outer regions of the galaxy, including our corner of it, for billions of years. And the instruments being built right now are about to give us a far clearer view of exactly how it does that. The galactic center has been studied for decades with increasingly powerful instruments. Every new generation of telescopes has revealed something unexpected. The pattern has been consistent. Better technology finds more mystery, not less. The researchers building the next generation of observatories are aware of this pattern and are designing their instruments specifically to answer the questions that current data cannot resolve. The Square Kilometre Array is the largest of these projects. When fully operational, it will be the most sensitive radio telescope ever built, spread across 2 continents with a total collecting area that dwarfs any existing facility. For the galactic center, it will do 3 things that current instruments cannot. It will detect individual millisecond pulsars in the central region by resolving their pulses despite the scattering caused by the intervening plasma. It will monitor transient sources like Andy's object continuously, catching every appearance and tracking the evolution of each active phase. And it will map the magnetic field structure of the central molecular zone in far greater detail, revealing how fields organize and channel material near Sagittarius A star. On the optical side, the extremely large telescope being built in Chile will carry a mirror 39 meters across, the largest optical telescope ever constructed. For the galactic center, it will track stars at precisions far exceeding what current instruments achieve. Orbital measurements that today require decades of observation will be achievable in years. If a star's orbit deviates from the prediction of general relativity near the center in a way that distinguishes a black hole from a dark matter soliton, the extremely large telescope may catch it. In space, the next generation of X-ray observatories will sharpen the maps of the galactic chimneys, trace the edges of the Fermi bubbles with higher resolution, and search for X-ray counterparts to transient radio sources like Andes object during their active phases. If Andes object ever produces even a faint X-ray signal during peak activity, a sensitive enough X-ray space telescope will catch it. The gamma-ray picture will also sharpen. Future gamma-ray instruments, including proposed upgrades to ground-based Cherenkov telescope arrays that detect the faint flashes of light produced when gamma rays strike the upper atmosphere, will improve the energy and spatial resolution of galactic center gamma-ray maps. The graininess debate over the gamma-ray excess will be tested with cleaner data. If the signal comes from point sources, sharper instruments will begin to resolve them. If it comes from a smooth, dark matter distribution, those sharper instruments will confirm the smoothness with higher confidence. Gravitational wave observatories add another dimension. The pulsar timing array, which uses precisely timed pulsars as a gravitational wave detector, has already hinted at a background of gravitational waves consistent with the expected signal from merging supermassive black holes throughout the universe. Continued observation will refine that signal and begin to separate contributions from different sources. If Sagittarius A star is not a black hole, future merger events involving galactic center objects will produce distinctive gravitational wave signatures that differ from standard black hole merger predictions. All of these instruments are either under construction or in advanced planning. None of them will produce definitive results overnight. Science at this scale takes decades, but the rate at which new information is arriving from the galactic center has been accelerating. Each improvement in instrument sensitivity has revealed new signals and new mysteries in less time than the previous generation required. The researchers working on these questions expect the next 2 decades to transform galactic center astronomy more dramatically than the previous 50 years did. And the thing that drives that expectation is not overconfidence. It is the pattern of what every generation of better instruments has found so far. Ask an astrophysicist who studies the galactic center what they expect the next generation of instruments to reveal, and the answer splits into 2 categories. The first contains things scientists are fairly confident about. The second contains a list of phenomena that current physics has no satisfying framework to explain, and researchers will tell you this openly. In the confident category sits the pulsar population. Most scientists working on the gamma-ray excess believe that millisecond pulsars exist in the galactic center in significant numbers, even if their exact count is unknown. The square kilometer array should find at least dozens of them directly. If it finds thousands, the pulsar explanation for the gamma-ray excess gains decisive support. If it finds far fewer than the model requires, the dark matter interpretation becomes correspondingly stronger. This is a testable prediction with a clear outcome, and researchers expect the answer within the next decade. Also, in the confident category, is a more detailed map of the galactic chimneys and Fermi bubbles. The energy flows, temperatures, and chemical compositions of these structures will be traced with much finer precision. The history of energy injection events from the galactic center will be reconstructed from those measurements, giving scientists a timeline of major episodes going back millions of years. This is complex but achievable work with known methods. The list of things without a satisfying model is more interesting. Andes object and its relatives remain genuinely unexplained. Scientists do not have a model that fully accounts for weeks-long radio transients, with extreme polarization and complete invisibility in every other wavelength. The leading candidates, magnetars, flare stars, and exotic binary configurations, each fail to match one or more observed properties. Researchers expect the square kilometer array to find many more examples of this class of object, which will help define its boundaries. But the physical mechanism may require theoretical ideas that have not yet been fully developed. The 511 kilo electron-volt positron excess has multiple potential contributors, and separating them cleanly requires spatial resolution that current instruments cannot achieve in that energy band. The exact distribution of positron production in the central few hundred light-years of the galaxy remains unmapped precisely enough to test the dark matter contribution independently. The correlation between the gamma-ray excess and the dark matter signals, if confirmed by future data, will need an explanation for why the dark matter density profile matches the observed glow so precisely. If it does not fit dark matter, the alternative needs to explain why the signal looks spherical and smooth rather than reflecting the clumpy distribution of known stellar populations. And then there is the question of what happened a few million years ago. The Fermi bubbles and the galactic chimneys both carry evidence of a major energy release in the recent galactic past. The exact nature of that event, whether it was a single, large tidal disruption, a period of elevated accretion, or something else entirely, is not pinned down. Future instruments mapping the chemical and temperature distribution of gas in the bubbles will try to reconstruct the timeline. Every expected discovery has a corresponding open question attached to it. That is the nature of a field at its frontier, and the galactic center, more than anywhere else in the Milky Way, sits at the leading edge of what physics currently understand. There is a specific kind of scientific moment that happens when a field is on the edge of something large. Measurements start disagreeing with each other in ways that cannot be explained by measurement error. Models that worked well for decades start producing predictions that real data does not match. Entirely unexpected phenomena keep appearing in new observations. The specialists in the field can feel the ground shifting before anyone can say exactly where it is going. The galactic center is in that moment right now. Every major instrument aimed at the core in the past 2 decades has found something that required revising an existing model or introducing a new category of phenomenon. The Fermi telescope found the gamma-ray excess that started the dark matter debate. The Chandra Observatory mapped the chimneys that revealed the scale of the black hole's energy output. The Australian Pathfinder found Andy's object and opened the question of an entirely unknown class of transient. The Event Horizon Telescope produced the first image of the shadow of Sagittarius A star and confirmed the existence of the compact object at the center, while leaving open the question of its precise nature. In the background, smaller studies have been steadily accumulating. The 511 kiloelectron-volt emission distribution has been measured more precisely. The star orbits have been extended, with some stars now showing subtle orbital precession effects consistent with general relativity predictions. The magnetic field structure of the central molecular zone has been partially mapped using polarized dust emission. Individual molecular cloud collisions near the galactic center have been imaged, revealing how the turbulent environment there drives star formation and stellar death on accelerated timescales. Each of these advances has been followed by new questions. The orbital precession of the stars, while consistent with general relativity, is also consistent with some alternative gravity models at the current precision level. The molecular cloud imaging reveals structures whose origin is not fully explained by standard turbulence models. The magnetic field maps show organized structures whose source of energy and mechanism of organization are debated. Scientists working at the Galactic Center are not frustrated by this accumulation of unanswered questions. They are energized by it. A field with no open questions is a field that has stopped advancing. The Galactic Center is producing new questions faster than existing instruments can answer the old ones, which is exactly the sign that something fundamental is waiting to be understood. The moment humanity is in, right now, is the moment just before the new instruments reach full capability. The Square Kilometer Array is under construction. The extremely large telescope is taking shape on its Chilean mountaintop. Space-based X-ray and gamma-ray observatories are in planning and development. Gravitational wave detectors are becoming more sensitive with each observing run. Within the next decade, the volume of high-quality data arriving from the Galactic Center will increase by a factor that makes everything collected so far look like a rough draft. What that data will show is not known. The researchers building these instruments have predictions, and some of those predictions will be confirmed. Some will be overturned by observations that no current model anticipated. History suggests the second category will produce the more important results. 26,000 light-years away, the center of our galaxy is pulsing, glowing, venting, and throwing stars into intergalactic space. It has been doing all of this for billions of years. Humanity has been watching closely for only a few decades, with instruments barely capable of piercing the dust wall. The picture we have so far is partial, contested, and extraordinary. The picture coming is going to change everything we think we know. We are paying attention at exactly the right moment, and the core of our galaxy is not finished surprising us.